So for the last section here in section 1.2, we're going to talk about graphing motion. So some people see graphing analysis make more intuitive sense than just the algebraic analysis of what's going on. So to analyze motion graphically, we have to first understand how graphs work. Now, I'm assuming you've gotten this in a math class before. We're going to do a very quick review. So we're talking about linear equations in this point. So we have a graph here shown in black. We have a line crossing it, and this is just a y-axis here and an x-axis. Again, this is just basic graph theory. Where the line crosses the x equals 0 axis, that point is called the intercept, B. The slope of this line is given by rise over run. How high does it go versus how far it travels to get to that height. So the slope, m, is equal to the change in height, the rise, over the change in length of the run. So rise over run is the slope. So we end up with our linear equation. The position y is equal to the slope of the line times position x plus the intercept b. This is just a general equation for lines. Now, let's apply this to motion. Below, in blue, I have a position time graph. So I'm going to have a thing go at a constant velocity in this simple graph. It's going to start off at some position x0, which is at time t0. So time is the x-axis here. This point is 0, 0, 0 position, 0 time. But you can see that the object isn't at position 0 at time 0. It's at some initial position x0. As time moves forward, the position increases until at some time t, it is at position x. So this initial position x0 is the same as the intercept in our earlier equation. The velocity, which is change in x over change in t, if you remember what average velocity was, well, the change in x is the change in height here on this graph. Of course, I'm not talking about height physically, but height on the graph. And the change in time here is the change the run. So the rise over the run is the slope of this line, which is the velocity. So rewriting, this is the equation I gave you in the kinematics portion. Position is equal to initial position plus average velocity times time. I'm going to flip those two terms here. Right. Flip these two terms, actually go this way so you can see. So I put average velocity and time first and the initial position second. So it's in the same form as the equation up here. Position is equal to the slope of this line times time, which is the x-axis component, plus the intercept. Now, we can look a little bit further. What if the velocity isn't constant? We're still going to look at a position time graph. So this is still time, and this is position. This position can be any axis, right? X-axis, y-axis, depending. We're doing one-dimensional motion still, so I'm going to pretend it's moving back and forth on the x-axis. So the position actually can be negative. Right? If it starts off at some point, maybe it reverses before going forward, or it goes forward and then it reverses. So I'm going to imagine an object that starts off at position x equals, we're going to say that that's 0. This is positive x up here, negative x down there. Time only moves in one direction, it moves forward. But I'm going to pretend this is the motion of the object. And it stops there. So the object moves in some positive direction, stops, stays at that position for a while, then reverses, swings down to some negative position, and then comes back up to some positive position. It's just random motion here, right? This is just arbitrary, I just drew it this way. But when we talk about velocity and instantaneous velocity, we can actually use this. So average velocity which remember is a v with a bar over it, is the slope between 2 points. So pick 2 points on this graph and figure out the slope that tells you the average velocity between those 2 times. Remember, average velocity is the change in x over the change in time. So let's say this is my first position, and then I want to know what is the average velocity between that and this position x. Or sorry, time t here, at position x. Well, I need the slope between those 2 points. So I have to draw a dotted line and figure out what the slope is between those 2 points. That will give me the average velocity. Well, if I don't want to do those 2 points? Well, that's a positive slope, so it'll be some positive average velocity. What if instead I want to know what the average velocity is between the initial position and that position? Well, I have to draw a line between those 2 points. I draw a line between those 2 points. The slope of that line is 0. It's a horizontal line. It has no slope, or slope 0. So the average velocity between that point and this point t here now, is 0. And that kind of makes sense if you think about it. The object went away, it had some positive displacement, but then it came back to its initial position at that time. So if I take a picture of the car at those 2 instants in time, when it starts and when it passes at that point, it looks like the car hasn't moved. If the car is in the same position, there's no displacement. If there's no displacement, there's no average velocity. Now, instantaneous velocity, or just velocity, is the slope of the line at some point. So while the average velocity between those 2 points is 0, I want to know what is the velocity at this point. Well, I have to draw a tangent line to that and then figure out what the slope is of the line at that point. That will give me the instantaneous velocity, or velocity. Now, slope is often calculus, right? Especially for curved figures, the slope of the line is the derivative of that line, the derivative of that equation at that point. Derivatives we're not dealing with, but graphically we could still look at what is a derivative, what is a slope. Now, the same thing is true for velocity time graphs. So if we have a graph of time and velocity, and we have some line here, this is our initial velocity at some time, it can be negative, at some time t0. At some later time t, we can talk about what is the velocity v. The slope of this line is the average acceleration. It's change in velocity over time, the rise over the run. And your book gives quite a few examples of going from a velocity time graph to position time graph to acceleration time graph and back and forth, back and forth. So you can, again, analyze more complex motion using these graphical methods. But most of the problems I'm going to be assigning deal with the algebraic solutions of these problems, not the graphing. I do assign a couple of graphing problems just to make sure you understand it, but the majority of the class moving forward will be algebraic analysis of these types of problems.